So let's start the topic of polyphase form of the QMF bank. Polyphase form of the QMF bank. So we have seen the two-channel Elias free QMF bank that can be efficiently realized with the use of polyphase filter. Basically, we are using a filter. So if we use a polyphase filter, that can be efficiently realized. Let me write down the two-channel Elias free QMF bank can be efficiently realized. Okay. So it can be efficiently realized. I'm giving emphasis on this with the use of polyphase filters. Okay. So I'm just giving emphasis on this. So you know that we have used the two filters, low pass and high pass. So one is H0 Z, other one is H1Z. So if we write H0 Z in polyphase form, say P0 Z square, Z inverse P1 Z square, and H1Z is P0 Z square minus Z inverse P1 Z square. Okay. So uh, we also know that just for the memory, that is h naught z, basically we have just taken it hz, and h1z is equal to h of minus z. Okay. We already know this thing. So this thing, we are just changing, we are just replacing the filter at the synthesis by this polyphase filter structure filter, and similarly uh, using Elias cancellation condition. Okay. So in the synthesis side, you can just write down G naught Z is equal to P naught Z square is Z inverse P1 Z square, and G1 Z is equal to minus P naught Z square minus Z inverse P1 Z square. Okay. So that's a thing for the Elias free reconstruction, or even using Elias cancellation condition. So we can just write down, and already you already know that, basically, as I already told you earlier, that for Elias free condition, what was that? It was h naught z is equal to, okay, hz, which is equal to g naught z. Okay. So g naught z should be equal to h naught z, so you can see from here. Okay. Additionally, I also told you that g1z is equal to minus h of minus z, and this is basically h naught. So if you translate and all those things, you'll be getting this. So not going into the further explanation. These two representation, these two first two equations and the second two equations can also be written in a matrix form. So let me just, for your sake of completeness, let those equations are, or in the matrix representation, you can just write it like this. So this is the column matrix which is equal to 1 1 1 minus 1 and P naught Z square and P1 Z square. Okay. So that's basically analysis filter bank of two-phase representation. And similarly, the second two pairs of equation you can just write G naught Z, G1 Z minus 1 P1 Z square P naught Z square. So that is multiplied with a matrix. It is 1 1 1 and minus 1. So that's a. So now let me just realize or do a polyphase realization of the two channel QMF filter bank on the next slide. Let's take some other color. Okay, so the polyphase realization for that is P naught Z square. We have P1 Z square, and here we have input Xn, and then a delay element by 1. That's the adder with a negative. Okay, then we pass to our downsampler. Okay, so this is the thing which we'll be getting at the output of the analysis section, and then we'll just pass it through to this part is the analysis section. Okay, analysis section. Then I will sketch here the synthesis section. So let me just complete that. In the synthesis section, basically, first what we'll be doing, we're just doing upsampling by 2. This is also upsampled by 2. Then so this will be something like this. P1 Z square, and this one is P naught Z square, and this is Z inverse. So this is your X cap and so using those two pair of equations basically, which I showed you, uh, we can just implement the quadrature mirror filter bank like this. And basically what we have done, we have just realized the filters in this way. And you can see this part, you can see a delay element is used, addition and subtraction as per those two equations which I showed on the previous slide, and this part also you can see. Okay. Now to further make it computationally efficient polyphase realization, what we can do is we can just uh, do an interchange process. We can just bring it on the left and we just shift this upsampler on the right. So and then using a Nobel identity, which I without explaining in more detail, I'm just sketching it. So first do a downsampling, then P naught Z, again a downsampler for the second channel. So here you have Xn, and this is the delayed version is going here. Then it will go to a header like this. So here getting output, and then this output will just pass it. So this part is the analysis section. This part is the analysis section. So that will go to a synthesis section. So in the synthesis section, so we will be just doing a little bit modification here. Let's just the negative sign here, and again applying a Nobel identity over here. So this is P1Z and this one is P0Z, then upsampler by 2, then upsample it by 2, then again a delay element like this. Okay, then add. So finally this is X cap n. So here the important thing which you can observe is that basically what we have done, we have just replaced, we have just bring this on the left, and when you are bringing it on this side, then again from here to here. Okay, so you need to apply a Nobel identity. Same for this case, actually you are bringing, let me change the color, this part from here to here, from here to here. Okay, so that's the thing we have done in the next this presentation. So you are just applying a Nobel identity. So here you can see the power of 2 is now, this is just a power of 1 in this case, power of 1, power of 1, if you remember the Nobel identity. So that's a efficient uh, realization or polyphase efficient realization of the two channel QMF bank. Okay, so let me write down, this is the polyphase realization of the two channel QMF bank. Thank you. So now I will discuss two channel QMF bank in sub bank coding. Two channel QMF banks in sub band coding. Okay. So let me first again sketch for you the uh, analysis QMF which we have just established in the previous slides. So we have seen that so this is the structure. Okay. So this structure is the analysis QMF. This one is the analysis QMF, and QMF synthesis QMF will be something like this. So this is X cap n. Okay. So this structure is for synthesis EMF. Okay. So now what we are going to do, basically we will be using these blocks. Okay, I will be using, I will be just writing it like this: analysis EMF block, and this one is just a box. With the box I will be representing synthesis EMF. So we'll be using these boxes in the subband coding. So let's see it on the next slide. You know that for a speech signal or any other one dimensional signal, what we do actually, we just first pass it through a low pass filter, then a high pass filter, then we do a downsampling by 2, downsampling by 2. Okay, then this one will be encoded. Okay, and this one is encoded. Then again for the high pass component, we do two things. We pass it through a low pass filter, then we downsample it. This is high pass filter, then we downsample it, then this high pass filter output will get encoded. Again for the low pass filter output, we will be having two components. The top one will pass through a low pass filter, and this one is a high pass filter. Again downsample by 2, and this one is again downsample by 2, then encoded, then this is also encoded, and this will, so these things will pass through a channel. Okay, so the output of the channel, from the output of the channel basically, so we do a reconstruction. Okay, before that, before going to the synthesis part, let me just tell you what is this. This is nothing. This is, you can replace this with analysis QMF filter, which we have studied. We have studied the polyphase form of QMF filter bank. So you can just replace this, which I had showed in the previous slide, analysis QMF. So this one can also be replaced. This block can also be replaced with the analysis QMF. Again, this part can be replaced with analysis QMF. So basically we need 3 analysis QMF filter, okay, for this case. And when after at the receiver, when you're using when the signal is passed through a channel or whatever you are doing, whatever you are storing it or whatever you're doing, so we will just try to reconstruct this signal from, so we'll be getting these 4 channels, and that will pass through a decoder. All these will pass through a decoder. Okay, then it will pass through a upsampler, then a filter. This is upsampled by 2. This branch is also passed through a upsampler, then a filter. Okay, then these two will get combined, will be added. Okay, then again this will pass through a upsampler by 2 and a filter, and output from here will also upsampled by 2 and a filter. Okay, then these two will get added, and this will be upsampled by 2, and then we do a filtering, and again this part will be upsampled by 2, then a filter. Okay. Then these will get added and produce the output. That's output. Now looking at this synthesis part, basically if you look at this is nothing. This is a synthesis QMF. Okay. Take this block. This block is again a synthesis QMF. If you take this block, this is again a synthesis QMF. So basically, here again you can see that you are using three numbers of synthesis QMF. Okay. So in this way, we can use two-channel quadrature mirror filter bank in sub-band coding. Okay, and these are whatever I have showed in the previous slide. All these are efficient realizations are there, so you can replace all these blocks with the efficient realization which I just discussed in the previous lecture, the previous slide actually. So all these things, all these blocks can be replaced with efficient realization. Okay? So that's the thing. Then the next topic is M channel QMF bank. Till now we have just discussed the two channel. Okay, so in general sense there may be a number of channels which may be discussing on the next one. Thank you.